Hi, everybody. I hope that you've had a first good day of school and things are going well. Just a minute before I made this video, we discovered that we're not going to be meeting until the end of February, beginning of March. So looks like we'll be doing this for a while. So please, 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 please feel free to send me questions by WeChat, and I'll try to organize a weekly question and answer time for everybody as well. But I'll work on that. Give me a little bit of time for that piece. So I'm going to start with a brain break tonight. I figured, or today, depending where you're at. Figured this might be a good thing just to do to keep your spirits kind of light. Insert two different pairs of letters into the blanks below to form two common uncapitalized English words. No answers are plurals. So let me give you a quick example here. Let's see. Oops, did I not turn on my pen? Oh no, oh dear. For example, for the first one, I don't think I can dare write right now without putting it the answers on, is probably cause, and then I can think of another word over here, caulk. So SE in the first two blanks, and LK in the second one. I'm going to hold my finger here in just a moment for 5 seconds. If you want to give the rest a try, please pause the video. Otherwise, I'm going to show you the answers in 5, 4, 3, 2, 1, 0. Pliant and plight, destiny and destroy, egress and excess, shorten and smarten, and then ampere and ampule. Ampule caught me. I couldn't figure that one out for the life of me. All right, let me turn on my pen this time so I won't forget. All right, moving forward. A quick review question before we get started. Is it possible, we were doing seesaws or teeter-totters before, is it possible to have a beam that's 1 meter long, that's 80 kilograms, on a pivot point? We've got 40 kilogram mass hanging from one side, but nothing on the other side. And you're like, well, you drew it in here. It must be possible. The answer is yes. What you got to do here is assume that the 80 kilograms, I'll draw it as 800 newtons, must be acting over here at the center of mass. And that is balancing the 400 newtons that are acting over here. And now the question is, what's x? And so this gets a little bit challenging. Just quick reminders, the distance to the center of mass should be half of the way there, so 0.5 meters. And so what's the distance between the pivot point and the center of mass? If you realize this distance is x and this distance is 0.5, you should be able to recognize that this is x minus 0.5. And then the other question is, what's this distance over to here? Well, if this entire distance is 1 meter, and this distance is x, I hope you can see that this should be 1 minus x. So how do we solve this? We know that the sum of the torques have to be 0. Or I'm going to draw another way here. The total magnitude of the torques counterclockwise must be equal to the magnitude of the torques clockwise. Now, just a quick reminder, normally counterclockwise torques are positive, clockwise torques are negative, and so the sum of these two the sum of all torques must equal 0 if it's in equilibrium. But I'm going to cheat just a little bit and simply think about it logically, where I ignore the negative signs for these and just say the magnitudes are the same. If you look at this situation, this force right here is going to tend to rotate this thing clockwise. So the clockwise torque's going to be 400 newtons times, where was my distance there? Oh yeah, 1 minus x. This distance right here has to equal this 800 newtons, which is trying to rotate the system counterclockwise. And so that force is 800 times x minus 0.5. And if you solve this, you should be able to get x. Let's see here. I don't have a pause button to record. So I'll let you solve this one, but you'll end up with an equation that looks like this: 800x minus 400 equals 400 minus 400x. Let's see, adding that to both sides. So I get 1200x, and then adding 400 to both sides equals 800. Or x is equal to 12 over 8. Or you could rewrite that, reducing that a bit. Sorry, taking me a moment here, as 3/2 of a meter. Whoops, sorry, pause there for a moment. I divided that wrong. Sorry, my bad. Equals 8 over 12, or 2/3 of a meter. That makes more sense. Sorry. I'm like, wait, it can't be greater than the length of the thing. So 2/3 of a meter. All right, moving on. Oh, I've got the answer there. What happens if you got a little bit more complex situations? We've been talking about equilibrium. Take a look at this. In this case, the worker here is standing on this platform. The pivot point's here, and the rope is making an angle down like this. And so what we've got here, here's the weight of the worker. The board is 300 newtons acting at its center. And the question is what's the tension over here? And we can also find R here. So I'm going to put the pivot point here. And so now I'm going to do that same little trick we did before, where the tension counterclockwise must equal the torques counterclockwise must equal the torques clockwise. We've got this tension over here, and that tension by itself would tend to rotate this thing counterclockwise. So my torque counterclockwise is going to be equal to the tension, which is a force, times the length of this thing, which is 5 meters, times the sine of 53 degrees. And now my torques clockwise are produced by these two things, which are both trying to rotate this thing clockwise relative to this pivot point. My worker is 600 newtons, and they're standing 1 meter away from the pivot point, plus the weight of my board, times the sine of 90, sorry, I didn't put that in there, times 300 times, how far is the center of mass away from the pivot point? If this is a 5 meter long board, that must be 2.5 meters. Solving this just real quickly, sine of 53. 53 is actually one of those nice triangles. It's a 3, 4, 5. So sine of that times 5, please forgive me if I'm wrong, should be 4 roughly. T equals 600 plus 600 plus a half of that, 750. Or we get 4t equals 1350 newtons. We're grabbing your calculator just real quick because I don't want to do this in my head. 1350 divided by 4. The tension is about, let's just go to 3 sig figs, 338 newtons. All right. Now, there's something else we can do as well, though. If this tension is 338, we can actually break it into its vertical and horizontal components. And I just want to show you this real quick because it's interesting. So 338 times the sine of 53 degrees. Oops. We do that one more time. Sorry, my apologies for the slight delay. You can do this as well. We get that this side is approximately equal to, let's just call it 270 newtons. And then this side, 338 times the cosine of 53 degrees gives us roughly 203 newtons. Now, you might say, why did you do this, Mr. Clymer? The question wasn't asking for it. Yeah, but believe it or not, you could even solve for r right now and tell me the angle. You're like, r? Yeah, the r is the force on this pivot point. You might say, that's impossible. Well, we can actually figure out its vertical and horizontal components, even though we don't know its magnitude yet. Why? We know that the sum of the two upward components must equal the total downward here. So the total downward force is 900 newtons. This is 270, about 300. So this has got to be 630 newtons. So the sum of these two upward components are equal to these. What's this horizontal piece? Well, since the tension is actually pushing in at 203 newtons, this has to be pushing out at 203 newtons. Could you actually figure out r at this point? The answer is yep. And could you figure out this theta? Oh, sure. Either using sine or inverse sine, inverse cosine, or inverse tangent. Cool. All right, moving on. Oh, I got the answer there. Good. Ladder problems are one of the banes of every physics student's existence. So what do we have here? We've got a ladder that's 10 meters long, and we're going to assume the center of mass is right at its center. And what we've got here is there's a normal force written as small n acting down here at the point where the ladder comes in contact. And there has to be a force of friction acting this way, static friction if you're curious. Otherwise, the ladder would simply slide away from the wall. In addition, there's another normal force pushing up here, which I'm going to label P just to avoid any kind of problems with trying to do the calculations. Now, some of the numbers. If this angle down here is 50 degrees, this angle up here has to be 50 degrees as well, opposite interior angles. And this angle right up here between the force of gravity on the ladder and the ladder itself has to be 40 degrees. So you can solve it. This is a nice right triangle. The complementary angle to 50 is 40. So solving this one. We have two unknowns here at the bottom part, normal force and the force of friction, although some of you might be able to guess it already. So let's put our pivot point down here. Why? Now I can ignore both of these forces when I'm trying to solve for the torques. Why? Because they're both acting directly at the pivot point. Again, remember, you can put the pivot point anywhere you want, just as long as it's convenient. So solving this one. So I'm going to go again do torques counterclockwise equals torques clockwise. And in this case, my clockwise torque relative to that pivot point, this 50 newtons would tend to rotate this thing clockwise. So that's going to be 50 times half the length of the ladder, that's 5, times the sine of 40 degrees. Sorry, I'm going to try to slip that in there really tightly. That's the angle again between that force and there. And then finally, that has to equal the counterclockwise torques, which is going to be P, which is kind of a strange letter, times the distance from the pivot point, 10 meters, that's the length of the ladder, times the sine, in this case, of 50 degrees. So solving this one, let's first of all solve for the force P. If you grab your calculators, give this a try. I know you're probably saying, oh, Ms. Clymer, I'll just let you do it, but go grab it. Pause the video if you need to. Sine of 40, all right, divided by 10 times the sine of 90. Or sorry, 10 times the sine, oh my goodness. 10 times the sine of 50. And if I trust my math, I guess I do. I get that P is equal to 21 newtons. Hopefully you got the same answer. I'm just debating myself. Yeah, it sounds about right. Believe it or not, we can solve the rest of this problem now. And you might say, wait a second, how could we solve it? If we know that P is 21 newtons, you can actually tell me what the force of friction has to be. Why? This system's in equilibrium. Not only does the net torque have to be 0, but the net forces. I've got this force acting horizontally this way. The force of friction must be 21 newtons acting this way. Same thing happens vertically. If the weight of this ladder is 50 newtons, this normal force here has to also be 50 newtons so that this matches this and this force matches this force. You might say, hey, Ms. Clomer, can I figure out what the force of static friction is? Well, kind of. Remember, the force of static friction, though, can actually range anywhere between 0 up to a maximum value. Is this the maximum value? The answer is I'm not sure. If it's just about the slide, then yes, you could actually work out mu sub s because you could actually do, whoops, you know that the force of static friction is always between 0 up to that maximum value. All right, good enough. Moving on. A conceptual checkpoint. Rank these situations from the largest to smallest force required to maintain equilibrium. So what you've got here is you've got some weight that's the same in each one of these. And the question is, how does this force compare to, let's just call this F sub g. And just for a quick example here, we know the torques have to be equal. So in this case, it's 2 units of distance times the force of gravity has to equal 4 units of distance times this applied force. And you can probably fairly quickly calculate, okay, my applied force is going to be half of the weight of this object. Why? Because I'm twice as far away. I'm only going to have to apply half as much force to keep in equilibrium. What about this case? You can probably quickly figure out, all right, it's going to be Fg over 4. This one, 3Fg over 4. I hope I'm doing these right. This one, Fg over 2, assuming that the board has no mass because we're not giving any information. This one, this one we're only half the distance away from the mass. This one is going to be 2 times F sub g. And the same thing here. So ignoring the weight of the board, which I assume we don't know, how would you rank these from largest to smallest? It would be E equals F, which is greater than, let's see, what are my next biggest ones? C, which is 3/4, which is larger than B equals D. Those are both equal to half, which is greater than C, which is whoops, whoops. Sorry, my bad. Hold on, what did I do? 3/4. A equals D, sorry, my bad, which is greater than, which is greater than C. Phew, wow, I don't have you guys here to check on me when I'm doing these. All right, quick note on this one. So in this case, you're like, okay, this is easy to solve. I've got 2,000 newtons times 1 equals the force times 3, have to equal each other, and you could calculate the force. But what happens if this is at some sort of angle? How would you solve it then? Which one requires a larger force, A or B? I'm going to stop for 3 seconds while you choose an answer in your head, then I'll tell you. Ironically, trick question, A equals B. You're like, what, Mr. Clomer, you're trying to trick us? Yeah, it turns out when you have it at an angle here, yes, this angle changes, but so does this angle. And it turns out these two angles are the same. So when you do the torque, force times R times the sine of theta for one equals force times R times the sine of theta for the other one, the sines cancel and you end up with the same ratio of forces as you had before, which makes it kind of fun. This is an old AP question from a few years ago, and this is why I brought up the whole angle thing. So how do you solve this one? Let's make gravity 10 again. So you can very quickly work it out. This is 1,000 times 1 must equal this force times 3. So this one's got to be about 333 newtons. This one, there's a 0 on there. This one we've got 1,000 newtons times 3. 3,000 equals 1 times this force. This force is going to have to be about 3,000 newtons. This one here, oh, you're like, oh, this is easy. 2 and 2, 1,000 newtons times 2 equals this force times 2. The force here, 1,000 newtons. This one, this time I've got 2,000 newtons times 1 is equal to the force times 3. And you should be able to work out, it should be about 600. I'm just going to go and call it that. This one, 2 and 2, 2,000 times 2 equals force times 2. This should be 2,000 newtons. And then this last one, 2,000 times 3, 6,000, equals the force times 1. This is about 6,000 newtons. And once you have that, you could rank them very quickly to about the force required for equilibrium. Largest one, by far, of course, F. Smallest one is A. Oh. I've got these batons at school, and I wanted to actually, normally what I do is pass them around. You'll have to forgive me. They're tricky. They weigh exactly the same number of kilograms, but inside of them, the blue one, all the mass is out here at the ends, at each end. And for the red one, the mass is actually on the inside, right about here. What happens if you hold them in the center and try to pivot them around this axis one way or another? You'll discover that the blue one is much harder to get started rotating and much harder to stop, whereas the red one is much, much easier. This idea we're talking about is called the rotational inertia, or the moment of inertia, depending on which text you read. Rotational inertia depends on the masses, but also where they're located. So if they're closer to the pivot point, you tend to have a smaller rotational inertia than if they're further apart. This one's harder to start rotating and harder to stop rotating. Just like regular inertia is how difficult it is to get an object moving, and once it's moving, how hard it is to stop. This one tells you how hard it is to get something rotating, angular accelerated, and how difficult it is to stop it, negative angular acceleration. So what's the analogy? You've got Newton's second law, F equals ma. The acceleration depends on the force and the mass. The same thing happens here. The torque and the rotational inertia determine the angular acceleration. The greater the torque, the greater the angular acceleration, the greater the rotational inertia, given the same torque, the smaller the angular acceleration. How do you calculate it? Simple calculation. Here it is. The rotational inertia of any object is defined as each piece of mass times how far it's away from the pivot point squared. In this case, I'll call that the radius. So the first mass times its distance from the pivot point squared, plus the second mass times its distance from the pivot point squared, plus the third mass times the distance it's away from the pivot point squared, plus yada, 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 yada. Or you can write it as sigma notation, just the sum of each piece of mass times how far it's away squared. And this equation works perfectly with discrete masses, that is, individual masses. If you've got continuous masses, that is where they're distributed throughout the region, I'll give you this equation down here. This one's for continuous masses, and it requires integration, or in other words, calculus to solve it. Do you need to know this bottom one? The answer is absolutely not. AP Physics 1 does not require you to know that, but I just wanted to show it to you for those of you who are like, hey, okay. So, mass, a measure how difficult it is to accelerate an object, speed it up or slow it down. Rotational inertia, how difficult it is to angular accelerate, increase or decrease rotational velocity an object. Real quick question, knowing the equation you have up here, which one of these two batons down below here, baton A or baton B, is going to have the greater rotational inertia if you rotate it around the axis here at the center? And hopefully you should recognize the one that has the greater rotational inertia is A. Why? Because the masses have a greater R, a greater distance away from the center here, both about 1 meter, than they do down here, where R is much smaller. Sorry, my pen's going bad. All right. So now some of the mathematical calculations. What is the rotational inertia of this object when it's spinning around its center? So here's our center. How would you calculate it? Oh, it's pretty nice. I is equal to the first mass, this mass right here, 1 times the distance away from the pivot point. It's this distance right here, which in this case should be 1 meter if it's 2 meters all the way across. Remember, that's squared. mr squared plus the second mass, 1 times its distance away, which is also 1 meter. And that's squared. And you'll discover the rotational inertia of this object is 2 kilogram meters per second. And you're like, oh, this is easy. Yep. What happens if it spins around one end? So now you're like, wait, what'd you do? The pivot point is now here. To solve this one, I'll call this I1. This one's now I2. For our new problem here, let's start again with this one, our 1 kilogram over here. And it's now 2 meters away from the pivot point. The whole distance all the way over to here. Plus our second mass, 1. And how far is it away from the pivot point? Well, its center of mass is right at the pivot point. So it's 0. What's the new rotational inertia? The answer is 4 kilograms times meters squared. Make sense? So moving the pivot point, even with the same masses and the same length rod, change the rotational inertia. It's actually more difficult to rotate it around this point than it was rotating around the center. All right. There's some other ones that are actually very easy to solve, even though they're kind of continuous masses. What's the rotational inertia of this thing? Well, since all the pieces of the mass, so imagine you took each little chunk of mass times the radius squared, you would discover that I was equal to m1 times r squared plus m2 times r squared plus m3 times r squared, yada, 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 as you work all your way around this, breaking this little masses. Or you could factor out the r squared, and you just end up with r squared times m1 plus m2 plus m3 plus all the other masses of the ring. Or you could just write it as, hey, wait a second, isn't that just the total mass, capital M, times r squared? And yeah, you're right. A ring has the rotational inertia of just its total mass times r squared. Pretty elegant. Let's do some other ones that are not quite as pretty. What's the rotational inertia of this thing if you would rotate it around the x-axis? You can pretty quickly see that these 3 kilogram objects are right on that axis. So the only thing I have to worry about are these two masses. Now, how far are they away from this axis here? Remember, we're rotating it around this x-axis. Well, if this is 0.6, I'm going to be really terribly lazy. And this is a right triangle. This is a 45, 45, 90. And if you remember, and I apologize to your math teachers already, I'm just going to write this as 0.6 over square root of 2. Remember, for 45, 45, 90, I'm going to write it up here on top. Remember, it's if this is 1, this is 1, this is 1 root 2. So working backwards, that should work. And the same thing is going to be true about this distance down here. In fact, this distance here and this distance here are all going to be that 0.6 over square root of 2. And I realized I could get rid of the radical in the denominator, but just because I know I'm going to square it in just a moment, watch what happens. What's the rotational inertia? I only need to worry about these two masses, this one here and this one here. And so my rotational inertia is just going to be 2 times 0.6 over square root of 2 squared plus 2 times 0.6 over root 2 squared. Oh, good grief. I wrote one thing and then wrote the other one. 0.6 over root 2 squared, which gives us, let's see, 0.36 over 2.18 times 2 is 0.36. So if I did my math right, it should be 0.072 kilogram meter squared if you rotate around that axis. In the same way, if we rotate around the y-axis, we would ignore these two kilogram objects, and the rotational inertia for this one would just be the mass, 3, times the distance away from the pivot point, 0.6 over root 2 squared, plus the other one, 3 times 0.6 over root 2 squared. And now I got to quick do my math. Sorry, I'm going to grab my calculator. Forgive me for a moment. 0.6 squared divided by 2 times 6, 1.08 if I did my math right. Kilogram meter squared. That's 1.08. And then finally, what would happen if you rotated around the z-axis? In this case, all of the masses now would be involved because they're all rotating and they'd all be this distance away. What would be the rotational inertia? You would actually have to calculate it by taking 2 times 0.6 over root 2 squared plus the other 2 kilogram times 0.6 over root 2 squared plus the 3 kilogram, times 0.6 over root 2 squared plus the other 3 kilograms times 0.6 over root 2 squared. Ironically, it should just be the sum of these two if I did my math right. Just double checking my math now. Yep, okay. Plus 1.08 should be approximately 1.8 kilogram times meter squared. All right. Whew, my finger's sore after writing all that. All right, moving on. Oh, good. So because you can't do calculus, the AP and your textbook will give you a table of the rotational inertias of some common objects. Now, it turns out we could solve this one by using a little bit of logic. So the rotational inertia of a hoop or a ring, even if it has some thickness this direction, is just mr squared. Remember, we did that a moment ago. For a solid cylinder, it's 1/2 mr squared. Why? It's a little bit less because some of the mass is actually located closer to the pivot point. Not all of it's at the outside edge like it is here. For a rod spinning through its center, it's just 1/12 ml squared. For a rod spinning through one end, where it's rotating around this axis, 1/3 ml squared. For a thin spherical shell, like a basketball or a tennis ball, it's 2/3 mr squared. And for a solid sphere, like a bowling ball or a billiard ball, it's 2/5 mr squared. Should you memorize these? Absolutely not. On the AP, they'll give you either this table or give you the rotational inertias. However, hopefully you'll start remembering a few of these just for speed, so you don't have to look it up each time. This table is in your textbook, and you'll see it quite often. All right. This next slide I threw in just because I thought, all right, a few of you might know calculus. I know about half of you do. For those of you who don't use calculus, skip this slide in the video. For those of you calculus, I'm going to go through this really, really quickly. I just want to show you where those equations you just saw came from. So here is a rod that's going to spin around that axis over there where that green line is. So starting with this formula, I'm going to measure x from that arbitrary starting point. And here's some little chunk of mass dm. So d in this case just means delta m, small chunk of mass dm. Now the question is what is dm equal to? Well, if you figure out this little chunk of the rod must be dx wide, if I'm using x as my variable here, what percentage of the total mass of this rod, which is m, would dm be? And here's where I'm going to cheat a little bit. See if this makes sense. I'm going to argue that dm should be equal to whatever fraction of the length I have. If this section is dx wide and the entire length of this thing is L, the fraction of the length I have is dx over L. And that should be the fraction of the total mass m that dm is equal to. That was the most complex part. From here on out, it's just straight calculus. Watch what happens. Plugging this expression in for dm down here, I get this. So replacing dm with this. M and L are constant, so I can move those outside the integration. My limits of integration, I'm going to integrate this from x equals 0 all the way to the end where x is equal to L. Doing the integration, you should know the integral of x squared is x cubed over 3. Think about it, the derivative of that would be x squared. With my limits of integration still 0 to L, plugging in my two limits and subtracting, I get this, or get that, which gives me that expression right there. You might say ml squared over 3. Yeah, that's 1/3 ml squared. If you look at the previous table, is what we got. Okay? So now we can do a couple of quick questions. My question is, and I'll show you a video in a split second, what would happen if I rolled a disk, a solid disk, a sphere, a solid sphere, and a ring down a ramp? And this is going to be a hollow ring, and I'm going to try my best to try to draw this, and I'm going to fail horribly. Oh my goodness gracious. That was a really bad ring. It's a hollow ring. If I roll these down a ramp, they all start out at the top all together. I can't draw them all together up here. And let them go. Which one's going to hit the bottom first? Now, because they have different rotational inertias, let's assume they all have the same radius and the same mass. Remember that a disk is 1/2 mr squared. That's how difficult it is to get rotating. A solid sphere is 2/5 mr squared. And a ring with all the mass at the outside edge is just mr squared. Because some of these are more difficult to begin rotating than the other ones, which one of these do you think would reach the bottom of the ramp first? And which one would be the most difficult to rotate and would reach it last? Are you ready? Video clip. And the answer is the solid sphere was first, followed by the solid disk, followed by the ring, which was last. Why? The sphere actually had the smallest rotational inertia, 2/5 or 0.4 mr squared. The solid disk was next at 0.5 mr squared, and the ring was last at 1 mr squared. It was the most difficult to rotate, therefore it took the longest to get itself down the ramp. You can watch the video again if you want in slow-mo. You can slower work your way through it if you need to. So how do you know which equation to use? The answer is think about it for a brief moment and then solve it. A bicycle rim would be mostly mr squared because almost all of its mass, the tire, is at the outside edge. A filled can of Coke, if the Coke moves with the can, would be 1/2 mr squared. It's a solid cylinder. A rod around the center, like a baton, like a cheerleader, would be like that. Baseball bat or tennis racket would be closest to this one. Basketball look closest to this one. A boulder, which is solid, probably closest to this one. All right. So now the math part. How do we use rotational inertia in actual problems? So in this question, what's the moment inertia of the spindle? Now you might say, whoa, the spindle here. Well, I actually give you a hint here. I said treat it as a solid cylinder. A solid cylinder is 1/2 mr squared. So in this case, 1/2 times the mass times the radius, 0.6 squared. Let's see, 0.6 times that, 3 times 1/2, 1.5. Oh, gracious goodness. 1.5 times 0.6. I get about 0.9 is our rotational inertia. Sorry, let me double check the math, just to make sure I didn't make a mistake. Okay, good. If the tension of the rope is 10 newtons, so this time I'm actually going to tell you that the tension over here is 10 newtons, and the tension here is 10 newtons. Remember, tension's the same on both sides. What's going to be the angular acceleration of this thing? Well, the rope unwraps from the edge of this, and I don't know if you can recognize this, but it's always going to be perpendicular to the radius. Our radius, again, 0.6 meters. How do we figure out the angular acceleration? Well, torque is equal to I times alpha. We know the rotational inertia. We can figure out the torque. The torque is going to be the force, 10 newtons, times the distance, 0.6, times the sine of 90, because remember that's a perpendicular one, so I'll just leave that out, equals the rotational inertia, 0.9 times alpha. So quickly dividing that, or solving that, we get 6 divided by 0.9, and we get that alpha in this case is equal to about 6.7 radians per second squared. What's the acceleration of the bucket? So the bucket, if you think about it, is accelerating downward. What's its acceleration? How is that related to alpha? If you remember back from a while ago, we can calculate it. Why? Because angular acceleration times the radius is equal to this. And you might say, well, what radius? The radius of the bucket? No, it's the radius of the spindle, the thing that's undergoing angular acceleration. And so if you take our angular acceleration, 6.67, times our radius, 0.6, we should actually end up with our acceleration, which I get, believe it or not, is 4 meters per second squared. That's not too bad. Finally, what's the mass of the bucket? You're like, oh, well, the tension's 10. It must be about 1 kilogram. Yeah, remember, it's angular accelerating, which means the weight over here, the force of gravity, has to be larger than 10. How do we solve this one? F equals ma is a good choice. So in this case, the net force is the force of gravity minus the tension, 10 newtons, that's that force up here, equals the mass, which we don't know, times the acceleration, which is 4. Force of gravity we can rewrite as 9.8 times m minus 10 equals 4m. Rearranging this just a little bit, you can sort of see I can add 10 to both sides, subtract 4 from both sides, and I get 5.8 m is equal to 10. So 10 divided by 5.8 gives us our mass, which is about 1. Oh, sorry about that. I hit the wrong button. Gerf. I still can't. Oh, no. How do I get rid of it? Now that I've done it. Yeah, oh, great. Sorry, forgive me for a moment. I can't get out of subtitles. Anyway, the mass, which I don't know if I can write or not, is 1.7 kilograms. Excuse me for a split second while I escape this video, or try to. Oh, I don't know if I can. Let's see here. Can I turn off? Oh, no. Ah, phew, that's much better. So 1.7 kilograms when you solve that one. Oh my goodness, I'll make sure I never hit that button again. All right. That was a fairly simple example. You're like, simple? Yeah, I'll explain why in just a second. I gave you what the tension was, and you could calculate the rotational inertia, and then the rest of it sort of fell into place. There's the answers. Here is a more typical problem. And I need to explain why this is a more difficult problem. The problem here is that we've got a rope wrapped around this cylinder. And what's going to happen is this thing is going to angularly accelerate. Oh, I shouldn't have gone blue on blue. It's going to angularly accelerate this way. At the same time, this mass is going to linearly accelerate downward. Here is the issue. Whenever you have both angular acceleration and linear acceleration in the same problem without any givens, like the tension, which is a critical piece, the only way to solve this one is by doing simultaneous equations or a system of equations. You're like, what? Yeah. In other words, you've got to do both F equals ma, Newton's second law, and the rotational equivalent of Newton's second law, which is this one here, the torque is equal to I times alpha. You're like, why? Well, how come we didn't have to do this last time? Well, because I gave you tension, and once you knew tension, you could solve angular acceleration directly, and then you could solve for regular acceleration directly. But without a nice given like this, we've got to do this the old-fashioned way. All right, so let's start with the linear acceleration part, this piece first. If you draw the forces acting on that mass, 240 times 9.8 is that, with too many sig figs. And the tension is the other piece, the tension acting there and there, which we don't know this time. So what can we write over here? We know that the net force on this object is going to be the force of gravity minus the tension equals its mass, 240 times the linear acceleration. And that's as far as I can take this side for now. How about this other side of the equation, torque equals I alpha? Well, the torque is going to be equal to the tension times the radius. Why? Again, I can't quite draw it because the rope's coming off the other side of this. But it's going to be acting at the edge of this thing, and it's going to be perpendicular. And so my radius is just going to be the radius of this, and it's going to be equal or times the sine of 90. So force times radius times the sine of 90 equals I. This is a solid cylinder, so 1/2 mr squared times the angular acceleration alpha. Please notice that this is alpha, this is a. And you're like, okay, no problem, plugging in the numbers. So I plugged in the numbers over here. And you're like, okay, good, we're set. So we've got two unknowns over here, tension and A. And over here I've got tension and, oops, alpha. Wait a second. That's three unknowns, alpha, tension, regular acceleration, and tension. I can't solve this problem. All right, here's where the little key comes in. You might remember from the Rosetta Stone, and we used it just a few moments back, that alpha times r is equal to a. If I know that, I can rearrange that equation and set it up so alpha is equal to a over r. If I do that, I can substitute it in over here for alpha. And now suddenly this is not so bad. And it turns out there's something interesting. If I plug in the radius here, 0.6, you get a very simple expression here. I get that the tension is equal to 300 times A. What can I do with this number right now? I can stick that back in for the tension over here. And now I can solve these simultaneous equations. Getting that, I can very quickly come up with the linear acceleration is that number. Once I have that, you're like, oh my goodness, I finally solved A up here, find the linear acceleration of the mass. The second question asks for the tension. You're like, oh man, it's actually not that bad. Why? I know the tension is just equal to 300 times A. In this case, that'll be 1310 newtons to 3 sig figs. And then finally, how do I answer C? What's the angular acceleration? I know that's just going to be equal to the regular acceleration divided by the radius, 0.6. And you can very quickly calculate it's 7.26 radians per second squared to 3 sig figs. These are going to be the most difficult type of questions you're going to run into this chapter. And so we'll spend our little bit of time with that. But after this one, I think you probably need another brain break. So here it is, my second brain break. Fill in the blanks below to make common uncapitalized English words. The letters you place in the blanks when read from left to right will spell out shorter words that can be preceded by the same word to form a common two-word phrase. Oh my goodness. All right. Let me do this first one. The only word I can think of would be foolhardy. Oh, and sure enough, those four letters do form the word lady. Don't worry about this first part yet. I think I've got this one. I have no idea what this one. At this point, if you need a little brain break, I'd recommend stopping the video and see if you can figure these out. I'm going to give you a countdown of 5, 4, 3, 2, 1. Okay, it was immature. Aborigine. Okay, psychotherapy, vegetarian, aborigine. I would have never gotten. So now we've got all of these words up here. This is actually a two-part quiz. The question is now, what word could you put in front of each one of these to make a common two-word phrase? And again, I think I've got it. I'm going to give you a 5-second countdown. 5, 4, 3, 2, 1. Boom. The answer is first. First lady, first mate, firstborn, first down in football, first step, first gear in your transmission. All right. All right. So this time, I want you to solve this on your own if possible, using these two things. Now, I'm going to pause it for a moment, and then I'm going to start solving it. But what I'd like you to do, and I know it's hard to try this on your own, grab a sheet of paper and see if you can't figure this out. Oh, I'm going to give you one thing real quick. The rotational inertia of a solid sphere is 2/5 mr squared. Could you please find just the linear acceleration of this mass as it's falling? Please, please, please try this on your own. Why? This is the most difficult problem. Yes, I know you could do it if you just watch me do it, but I need you to try it once before I solve it. And I pause it here. When you're ready, start it again. All right, welcome back. So drawing the forces on this one, I've got 19.6 newtons acting downward here. The tension acting upward here. That same tension, please just redirect it, is acting here. So solving this one, first of all, net force is going to be 19.6 minus the tension equals 2 times A. And that's as far as I can take it for now. Solving this one up here, that tension is going to be acting at this radius, and that's going to be perpendicular. So the tension here is, the torque here is going to be the tension times the radius, which is 0.2, times the sine of 90, which I'll leave out, it's 1, equals 2/5 times the mass times the radius, 0.2 squared, times the angular acceleration. And forgive me, I'm going to quickly replace that with A over R, just because we know we're going to have to do that. Real quick, if you haven't noticed already, the 0.2 cancel out one of the 0.2s here, divided by 0.2 cancels out the other one. And so I very quickly end up with the tension here is equal to 20 over 5, 4A. Substituting that into the other side, I get 19.6 minus 4A is equal to 2A, or 19.6 is equal to 6A. Grabbing my calculator, 19.6, I know you probably solved this already. Oh no, my calculator just went dead. Oh, sorry, 19.6 divided by 6, and you get about 3.27, which is the correct answer. That's how fast this mass is going to accelerate downward. Yes, once you have that, you could find the angular acceleration, you could find the tension, you could even calculate the time required for the mass to fall some distance. All of these things are easy once you solve this. Notice that the equations seem to get much easier this time, hopefully, but you'll have a few practice ones like this in your homework tonight. My last piece, and to finish up tonight, or today, is the parallel axis theorem. Parallel axis theorem is crazy powerful, and I can't prove it to you, but it allows you to find the rotational inertia of continuous mass objects, even if the pivot point's not in one of the positions given on this diagram. So, for example, if it's right in the middle here like this, you're like, okay, I can just look it up. It's 1/12 mr squared, and plug in the numbers. In this case, meter stick is 1 meter long. And you very quickly, if its mass is 1, you can solve it. And if I move the pivot point to the one end over here, you're like, oh, okay, that's this one right up here on the table. That's just 1/3 ml squared, or that. But what happens if you move the pivot point to some other spot, in this case at the 30 centimeter mark? How do you solve it then? And the question is, what's the rotational inertia? Well, it turns out it's equal to this, and I'll explain why in just a second. The parallel axis theorem states that the new rotational inertia of the thing is equal to whatever the rotational inertia was of that object when it rotates through its center of mass, plus m times h squared. And you're like, what is this h thing? Well, here's how you solve it. That's where I talked about. And this, the h is the distance from the new axis to the center of mass. So how would you solve it down here? Well, the center of mass is over here at 50. If I'm rotating it at 30, my h is this distance right here, which in this case is 0.2 meters. So how do you solve this beast? You're just going to take 1/12 ml squared. That's the rotational inertia if it's rotating through its center of mass, and add in its mass times h, which is how far the new pivot point's away from the center of mass. It's crazy useful and also crazy powerful. You can calculate the rotational inertia of this meter stick is now 0.123 kilogram meters squared. What would happen if I moved it to 0.4? In this case, h is going to be what? It's going to be 0.1 meters. Could you please pause the video and solve this before I show you the answer? And here we go. Yeah, you should have gotten 0.0933 kilogram meters squared. It's smaller than it was before. What happens if you have a basketball and for some odd reason you're spinning it around the axis like this? I don't know how you would do that actually. You have to glue a stick or something to one end. How do you solve it? Well, basketball is a hollow sphere, so 2/3 ml squared. And what's happened here? Our center of mass is right here. So what's h going to be? H is going to be equal to the radius, since that's also how far it's away. How do you solve this one? Go ahead and see if you can solve it before I show the answer in 3, 2, 1, go. So the original rotational inertia, 2/3 mr squared, that's this number right here, plus m times h squared, where h again is going to be equal to the radius of this basketball, and you should end up with 0.150 kilogram meters squared. And believe it or not, we're done for the day. Have a great night. Give the textbook problems a try. Again, remember to submit them to the Canvas Dropbox when you're ready. Ask me questions in the WeChat group. I promise I'll try to catch myself up on those. I'm not up to date, but give me a chance. I'll work on those. Have a great night. Talk to you soon.